So first, let's talk about stacks. A typical list is just a series of values in some order. They have some indices associated with them. And at any given time, we could do something like request the second value and load it into somewhere else in our code. A stack changes this model a little bit. With a stack, instead of it being like all our values are in a single row that we can access at will, it's as if they're stacked one on top of the other. Think of it like stacking boxes. What makes this important is that at any given time, if we have a new item to add to our list, the only place we can add it is to the top of the stack. We can't just insert it somewhere in the middle. Half the definition of a stack means that we can only add new data to the top. And the other half is that the only data we can access is the data currently on the top. We can't directly access anything but the topmost data. And in many implementations of stack, we can't even look at the topmost piece of data without actually taking it off the stack. So it's kind of like saying we can't open a box unless we take it off of our stack of boxes. For this reason, a stack is also called a LIFO, which stands for last in, first out. The last item added is the first item removed. That's because the last item added will always be the topmost item, and we can only ever remove the topmost item. Now, it might sound kind of weird to limit ourselves like this. Why would we want to only access the topmost item when we could just use a list that lets us access any item? Now, some reasons for doing that are actually historical. Some older computers or some older programming languages were really inefficient or really slow, and so it was a lot faster to know that there was only one item that could be accessed at any given time. However, stacks actually come up a good bit when you're dealing with real computer programs. Imagine, for example, you were programming a robot to search for your keys in your house. To do that, it might do three things. Search the kitchen, search the bedroom, and search the bathroom. So this is kind of like a stack of tasks. But the reason why it's useful to think of this as a stack is that each of these individual tasks probably unpacks into multiple individual tasks. For example, search kitchen is probably made out of search the counter, search the cabinet, and search the drawers. When you tell the robot to search the kitchen, it goes to the kitchen, and then it runs these three commands. But it makes most sense to add those three commands to the top of the stack because you don't want it to leave the kitchen and have to come back later. And so at any given time, you can visualize a stack of tasks for the robot to complete. Whenever a new task is encountered, it's unpacked and added to the top because you want it to do it right away. It's only once it's done everything in the kitchen that you want it to move on to the next task. So you always want the new tasks to be added to the top of the stack. To a large extent, you can even think of the regular code that we write as implementations of stacks. For example, imagine we had a function called print 3 lines. And all it does is print 3 blank lines. Our main code then might call that function twice. This is like a stack of commands to execute in order. Execute the one on top first, and the one on bottom second. When we execute the one on top, we're basically making a copy of those three commands and adding it to the top. At any given time, we only run the topmost command. So if we've just added those three commands to the top, then we'll execute those three first, before ever executing the second call to that function. When we execute the second call, it'll again add those three to the top of the stack. So in many ways, this is exactly how code runs. Code executes commands, and one of the commands it could execute could add new commands to the top of the stack. At any given time, the computer only runs the top command on the stack.